The truth of the matter is, much of what I have here on this left-hand board is what I had on the right-hand board last time, but of course we didn't get to it. So what we'll do today is we'll finish up that story on the action potential, and I'll spend some time showing a couple of slides trying to divine the idea of propagation in unmyelinated axons and compare that to propagation, action potential propagation in myelinated axons. And then what we'll do is then we're going to begin setting up a new idea. What we're going to do here is we're going to talk about generating a generator potential and then producing an action potential from that generator potential and then carrying that information to a synapse. We're going to initiate this idea by using the input region. If you put your phone away, I'd appreciate it. And we're going to use the input region of a sensory neuron in such a way that if we change the shape of that sensory neuron input region, we will now open stretch-activated channels, and the opening of the stretch-activated channels will allow sodium to come into that cell. Now, we're going to see this is a two-step event. The first thing that's going to happen is we'll see that the amplitude of this so-called generator potential, and the generator potential is a result of opening these stretch-activated channels, and we're going to see the amplitude of this potential is proportional to the strength of the stimulus. But one of the major ideas to carry away from this, and combined with the story from yesterday, is that these generator potentials, no matter how large they may be, because they don't themselves involve voltage-gated channels, don't propagate very far. So that means there has to be some interface, some communication between the generator potential produced by the influx of sodium through the stretch-activated channels and the voltage-gated channels we talked about yesterday. We'll see that there's a region out near the tip of your finger, near the end of that input region of the sensory neuron, where there are located clusters of voltage-gated channels. Not so different than the clusters of voltage-gated channels we saw yesterday at the nodes of Ranvier. Same idea. We're going to bring them together in one small spot. So now the electromagnetic fields of the sodium, which are being delivered because of the stretch activation of the membrane, by pulling on the membrane, by deforming the membrane, that depolarization, that increase in positive charge will be now interpreted by these voltage-gated channels, and the voltage-gated channels will open. That then will generate an action potential, and we now have a long-distance signaling system. So now we can conduct that information from the tip of your finger into your central nervous system. We're now going to use the stretch-activated channels to initiate action potentials that will propagate over long distances. This brings us to an interesting problem, because one of the ideas that we saw yesterday and that we'll drive home again today is that the action potential itself is an invariant potential. That is, it's almost always the same amplitude. It's almost always the same duration. There really is very little difference between one action potential to another. Now, it's true the generator potential can vary over a broad range, but the action potential is a fixed kind of signal. So how do we carry information over long distances using this fixed stereotyped signal? Well, what we do is we encode the information in the frequency. So once we've exceeded threshold, these action potentials will tend to fire for some period of time. The stronger the stimulus, the farther above threshold the membrane is, the more frequently these action potentials will fire. So now we have built within this a duration of the action potential. We have built within this a duration of when the action potentials can be firing, and within that bout, within that duration, we can then see that there is a frequency of action potentials. So now we're encoding the information in the duration of the bout and the frequency of the action potential within the bout itself. But of course, all of that is signaling within a single cell. And the nervous system, of course, put your phone away, please. And within the nervous system, there has to be that's you, yes. If you would, please put it away. Thank you. Where was I? So the idea here is this is all within one cell. But now we have to think about the delivery of this information to another neuron. And the delivery point between one cell and the next is at a chemical synapse. This is an idea that falls out of the neuron doctrine. If the neuron doctrine is telling us that the nervous system is constructed from individual units called the neuron, there has to be some mechanism of communication between those neurons. One of the ideas that Golgi and the other reticularists could never reckon with was how you got communication from one cell to the next. They didn't believe in cells. It just looked like a giant gamish to them. But now with this insight that we have chemical synapses, now we begin to see an ability to regulate communication from one neuron to the next by the release of neurotransmitter and the effects of that neurotransmitter on the next cell. So we're going to spend a fair amount of time talking about the chemical synapse. And I want to give you some idea of where this idea came from because it's fundamental to how the nervous system functions. And as we begin to learn more and more about learning and memory, we begin to learn more and more about how the nervous system takes information in and codes it and does something with it, we have to understand more and more about the synapse. So I want to spend some time talking to you about where that all came from. But there are two ways we're going to talk about it. We're going to walk our way through it first in terms of the chemical synapse and its pharmacology, neurotransmitters and the receptors. And then we're going to talk about it in a more recent way of thinking about them, and that's structurally. That is, the first will just be what are the chemicals doing and how do they do it. And the next part is to begin to drill down into the structure of the synapse and think about how its structure influences its function. And we'll talk in some detail about that.